Okay, today we finish chapter 4 and start studying chapter 5. I hope it will be fun, especially in the second part of the class. In the first part of the class we are going to see the pictures from chapter 4 and maybe discuss them for a moment. Maybe some new ideas come to us. And we are also going to go fast through the chapter 4 and see what we didn't study yet. Probably there will be just a few topics more. Good. We also said that among the elements, there are not so many gas elements, only those on the blackboard. And of course, the rest depends on the temperature. When I was learning how many metals there exist in the periodic table of elements, there was of course many of them, but I mean solid metals, or how many liquids exist in the periodic table of elements. I was taught the only one, bromine. But I guess in Taiwan they are teaching you there are two of them. There is one of the metal that has very low melting temperature. If I remember correctly, it's gallium. It's 32 degrees. So I guess in Taiwan in summer it's a liquid. So everything depends on your point of view. But with the gas form, of course, again, it depends on the temperature. So the bromine would be gas if we are living in higher temperature world, but we don't. So among the elements, only those are gas. But you know that many connections of different elements together make also gas particles. We are not going to stop here for long. This is a very nice picture, I like it, from your book. This is the Earth, the solid part, and here is the gaseous part of the Earth. So atmosphere. We already know that this part is not very wide, maybe 30, 50 kilometers. But that one that you can see, the clouds are usually up to 10 kilometers. So this is maybe another 20 and another 20. Last time we were asking what is the free path of a particle be around 100 kilometers from the Earth. There, where hardly any other particles are. And it was around 100 kilometers. Okay, here is the picture showing the definition of a pressure. When the particles hit to the wall and bang back, all the time they are pushing it in the one direction. Since you see that in all possible walls of this tank, the same collision happens, the pressure in all possible directions is the same. When the tank is very big, this is going to change, and we are going to discuss it for liquids a bit later. These are the pressure of the pressure units of pressure, and you should remember them, unfortunately. These are important things for the exam. So especially Pascal and bar atmosphere. These torr are not so important, but they still may come in the exercises. Okay, so I don't know if they are showing it here, but that's a typical picture from the weather forecast in my country. So they are showing this map and they're saying, okay, high pressure here, people in Russia today feel good. And again, low pressure in Great Britain, British are having not good moods today. So it really happens. So you have it in your textbook. I'm collecting the countries that have this correlation. So far only Poland and Bulgaria say they have this correlation between pressure and feeling. If you have some other countries, tell me. Well, I don't know why I put this one here. We skip this. Okay, this is we're studying two laws for the gases. One of the laws was saying that pressure times volume is constant. So you see that the curve for a system makes a form like that. It's much nicer to plot it if you plot not against volume, but against 1 over volume. Then it's just a straight line. It's easier to remember this. But still, they are simple laws. Okay, this picture is showing that when you take a tank and you change it to the half size, then the two collisions that were happening in the big tank, because the molecules can go all the way around, now there will be 4 of them, and the pressure will go twice larger. This is a similar curve between the volume and temperature, again the next law that we studied. And that's what I said before. If we have different gases and we have the volume, temperature dependence, all of these curves, they will meet in one point, which is the definition of the 0 Kelvin. They would meet if there is no liquefaction on the way. No, nothing new. Oh, this is interesting. This is showing how much the volume of the gases is changing for 1 mole. When we have ideal gas, it's 22.4, but when we are going to something what is not so ideal, like here, argon, we see that the difference is much, much larger. Again, around all of them are around 22, so no such a big difference. Good. Again, maybe you shouldn't remember these numbers for the exam, for the final exam. But what you should remember is what are the units, and that there are different units. So don't try to solve exercises when these units are different than the data in your problem. I know it's stupid to say it, but many people try to do such things. Okay, this is the volume of 1 mole of gas. You see, it's not very big. It's 22 liters. By the way, inside this box, there is 10 to the power 23 atoms. This is huge. And there is still a lot of space between them. So you really see how small, how tiny are the atoms. Okay, again, you should remember these things, that depending on the temperature and depending on the pressure, the volume of 1 gas, 1 mole of a gas, of an ideal gas, is different. And you should remember these numbers, unfortunately. At least you should remember 22.41, and you should remember 24.46. This is important for solving exercises. I like this part. This is saying how much different elements in the air around us. So we have 78% of the nitrogen, 21% of the oxygen. So you see that these gases make a 99% contribution to all the air. The carbon dioxide is very tiny, small part. But now recently, during last years, it's increasing up and up. But still, it's very, very tiny, but it's making such big problems. Let's go further. With this one, be careful. Sometimes people are saying what is the volume composition, but sometimes they are referring to the mass composition. If the mass of nitrogen and oxygen are the same, there is no difference, but they are different. So you see that 75 versus 78, 21 versus 23. Just be careful about this difference. Okay, this is interesting. When you have molecules reacting in a gas phase, for example, when you have molecule A reacting with the molecule B, and usually we put here G to represent it's a gas. And they give you molecule AB that is also gas. You can put here N, and you can put here M, and you can also put this NM here. you see interesting things. For example, when you take 1 mole of N2 and you react with 3 moles of H2, then you get 2 moles of NH3. What does it mean? This means that 1 mole plus 3 moles gives you 2 moles. But now if we assume that the temperature is 25 degrees and the pressure is 1 atmosphere, we have that 24.5 liter reacting with 73.5 liter give you 49 liter. If you add this together, it's probably 98 liters, going to give you 49 liters. So before, the volume was 98 liters. After the reaction, it went half down. Why is it important? It is important because there are 2 words. One is called explosion, and another one is called implosion. That means a reaction when the volume changes fast. This case is an implosion because the volume went down. When you have other case, when you have some small volume, you get large volume, that would be the explosion. Okay, and we are going to see some examples here. Oh, this is another interesting idea. How to remove carbon dioxide from the air. So usually what is used is potassium superoxide, the yellow thing, the yellow solid, and you just push air with carbon dioxide through, and you see that it's changing into usual carbon oxide. And this is the potassium oxide on the walls. So this is a very interesting reaction. And this is another thing. This is the explosion of the carbon powder. So we again are here. And why the explosion is such big? Because in this case, what is happening, you have carbon solid, this is the important part, plus O2 gas. And they are going to do CO2, also gas. So you see that here from 24.5 liter, also you have 24.5 liter, but you have also a lot of energy, heat. And this heat is going to make this one very hot. So you know that dependence between temperature and the volume, this volume will be rapidly expanding to match the temperature, and you have the explosion like that. Very spectacular one. This is another reaction of the same size. What was the element? It's N3, but potassium, I have to check this, sorry. Sodium. Sodium N3 is a solid, but it rapidly decomposes into Na2O plus oxygen. Of course, it requires some water. Maybe just air from the air. So just O. So you see that before the reaction, it's solid. But after the reaction, almost everything is becoming gas. So a very small volume of solid is rapidly expanding into large volume of gas. And the gas is N2 inside this safety equipment in a car. Here is another rule. When we are mixing two different gases together, so gas A, which is red, and the gas B, that is blue, and one of them has the pressure 0.4 and another pressure 0.6, after mixing, the pressure just add together, PA plus PB. This is very easy to imagine. So just simple addition of pressures for mixture of gases. Okay, here is also a good moment to introduce the new term called partial pressure. And you have that the total pressure is the pressure of PA plus PB. So now we are defining something what is called molar fraction. So it's number of mole of A to the number of moles of everything. So in our case, of course, this is equal to NA plus NB. And we also can define XB, which is going to be equal NB to N total. We can play with this one a bit. We take NA and multiply it by RT. If we multiply, we also have to NA plus NB, multiply the denominator. We divide it by PV. Just by V. Yes. And now the upper part is just the definition of PA. The lower part is the definition of total pressure. So from this one we are getting that XA, the molar fraction, is PA over P, or saying in other words, the partial pressure of the gas A is equal to the molar fraction times the total pressure. And similarly for the other component, we have XB equal PB over P, and from that one we are getting that PB is equal XB times P. This is true only if A and B are gases at the same time. Otherwise, we cannot just simply use this form because the ideal gas law doesn't work. Okay. Let's go further. Okay. Here you have an interesting thing. We have a wall and we make a hole, very small, very tiny hole inside. And some particles of the gas, they are coming to the wall and bouncing back, but some of them find the wall and go outside. Now what happens when they go outside? Well, you can think that when they are inside, the distance between two particles is some, and there is interaction between them. But one of the particles go outside, the distance becoming very large. So because of the interaction with other particles, these particles slow down, and moves very slowly finally at the end. How to understand this? To understand this, you should draw a potential energy curve. This is interaction two particles. And we have one of the particles being here, and the other particles, let's say, being here. So that's the potential energy between them, V. But now we know that the total energy is the kinetic energy plus potential energy. So now, when one molecule is getting out through this hole and going very, very far, it means that the distance between molecules inside the box and molecules outside the box is going to be larger and larger and larger. So you see that the potential energy goes up. Okay? But the total energy is constant because the molecule doesn't interact with anything. If the total energy is constant and the potential energy goes up, it means that the kinetic energy must go down. It means if the molecule is getting farther and farther from all other molecules, then it slowly slows down. And then the molecule slows down, also the temperature goes down. So this effect was used a few slides later. We can, I guess, forget this one. This one wants to say that when you have ideal gas model, the collision happens in one single point. You see that the curves are sharp. It's 90 degrees, or it's a sharp angle. While in the reality, the molecules collide something like this. This is the real collision. Here is the ideal gas collision happening in one single point at 0 time. Here we are calculating the number of molecules that hit the wall in some time, and we defined the length of the interval as Vx times delta t. And the idea was that everything what is inside at this time will hit the wall, but what is outside will have not enough time to go to the wall. And this plot we discussed last time, this is the speed of particles of gas. So you see that the hydrogen is the fastest in the room temperature, and the other molecules are much slower, but still very fast. This is the distribution law of velocities, so-called Boltzmann law, and for different molecules. It's for a molecule that is very light, 20 gram per mole, so the molar mass is small. And for molecules that are heavy, 100 grams per mole. You see that the light molecules have larger distribution of speeds. It means that they can go faster than the slow molecules that can go only slower. But the kinetic energy is the same. How to measure this thing? Usually they make some so-called slit experiment. It's a wheel with one small hole that the molecule can go through. If the molecule can go through this hole and then it has wrong speed, it will hit the wall. But when it has the speed related to the rotation of this thing around, it will go through all of them and finally hit the screen. So you can just measure how many molecules have which speed. Very nice experiment. And that's the results from this experiment. For every rotating speed of this experimental equipment, you are just measuring what is the intensity of the signal on the screen. And you again see that at different temperatures the speeds are different. In low temperature the speeds are going to be small. When you go to high temperature it's going to be much wider curve, which is what we expect. We know that the temperature and the velocity are correlated. Here we have the departure from the ideal law for gases, defined for the compression factor. We defined it at the last class. Okay, and here we are coming again to the mechanism of liquefaction of gases. So when you want to liquefy a gas, you are just using this separation. When the potential and the molecules are getting farther and farther from each other, the potential energy goes up. So for example, what you can do, one thing that you can do, you can use very low temperature to liquefy the chlorine. So you're just putting the gas inside, the gas is around here and escaping, and here is very cold region. And when it's touching the cold region, it's becoming liquefied and finally drops down. So this is one way, by making the temperature lower, but it not always works. And when it doesn't work, you have to use this one. You have to make the molecules slow down when they are getting farther and farther from each other. And this one is used, for example, in the fridge. You have the molecule with some pressure, and then they are suddenly, through the very small hole, getting to the large volume, and they go all directions, and when they go all directions, they slow down and liquefy. Okay, we said that there are many different models of the real gas equations, and one of them was the van der Waals equation. These are the van der Waals parameters, A and B. Again, I personally don't like this equation, but people very often use it, and they say that parameter A corresponds to the attraction between molecules, and parameter B corresponds to the repulsion between molecules. You should remember this part, that A represents how much they attract each other, and B how much they repulse each other. This is a very typical question at the final exam. What is the meaning of A and what is the meaning of B? My understanding is there is no meaning, but very often people say attraction and repulsion. You should go through the books now and ask me questions if you have any questions to chapter 4, because we are going to finish.